In this video, we are going to look at PlantPAx System Release 5 from an operator's viewpoint using Emulate 3D for the process plant simulation. We will start with looking at the HMI framework provided with PlantPAx and how this allows you to implement the ISA 101 standard recommended display hierarchy if you wish. Then we will look at an analog input, valve and motor, HMI object and faceplates. I'll show how easy it is to fault find and how the organisation tree aids in quickly finding where faults are in the system. I'll then explain the device ownership and security model used by the PlantPAx library. And finally, I'll show the device statistics and command confirmation options available. PlantPAx System Release 5 and the Library of Process Objects version 5 comes with a HMI framework that allows you to quickly implement your HMI for your PlantPAx system. This framework is based on ISA 101 and allows you to follow that standard if you wish. Here you can see an example of a level 1 overview using the PlantPAx framework. The ISA standard gives a recommended way of structuring your HMI into different levels. Here we can see an example of those different levels. The HMI framework provides this banner that you can see at the top of the display, and it provides a number of pre-built buttons and displays to help you get your HMI application up and running quickly. As well as these pre-built screens and the navigation menu at the top, the PlantPAx framework then also provides pre-built template navigation buttons for building the navigation of your HMI. At the top here you can see we have a set of navigation buttons which take us to the level 2 displays for each area in your system. If I select the level 2 here, then we can see an example level 2 display for my batch tank area of the plant. The HMI framework also includes displays for our level 3 displays and their templates we can then fill in with what we need. So if we go and have a look at our batch tank example, we can go directly then to the level 3 display for our premixer. This part of the plant is using FactoryTalk batch to control it, so as well as showing the PlantPAx library objects, we also have the controls showing us what's going on with FactoryTalk batch for this area of the plant. Currently they're empty, there are no batches running in the system and there are no batches running on the premixer that we're looking at here. We have similar displays then for the other premixer and the reactors in our plant. In the feed drum area, if we go to our level 3 display, we see our level 3 display that's based on the PNID for the feed drum with all the details. In the library of process objects, you have a large array of instructions to cover all the things you typically come across in a process control application, as well as frameworks for implementing sequences. You also get a large amount of instructions for connecting to instrumentation via Ethernet RP, via Profibus PA, and via Foundation Field Bus. You have instructions for doing steam calculations, and you have instructions for interfacing to electrical protection devices via the IEC 61850 protocol and via Ethernet IP. Let's start with an introduction into an analog input, valve and pump in the library of process objects. On this display we can see an example buffer tank process. Here we can see a HMI symbol for an analog input, a HMI symbol for a valve, and a HMI symbol for a pump. We can also see another example of a HMI symbol for an analog input. The library provides a number of options for each of the instructions available in the library. For each of these HMI symbols, we can click on them to bring up their quick displays. Here is a quick display for an analog input. Here is a quick display for a valve. And here is a quick display for a pump, which is using the variable speed drive instruction in the library. The quick display shows key status information to the user and allows you to control the device where you have the permission to do so. Here on these quick displays we can see the current status information. We can see for the analog input that it's currently in a normal operating state, its current temperature, its units, and we can see a trend of its temperature over time. For the valve we can see it's currently closed, and for the variable speed pump we can see that it's currently stopped. On the quick display you'll notice that there are tooltips to give us information about what the buttons do. For each HMI symbol, you can decide whether the quick display is displayed or the full faceplate is displayed, which we'll have a look at in a minute. You can also decide if the faceplate displayed is based on the current user level of the logged in user. It can be the quick display for users which are at an operator or operator supervisor level, and the full faceplate for higher level users. Let's now take a look at the full faceplate for an analog input, a valve and a variable speed pump. Here is the full faceplate for the analog input. Here is a full faceplate for a valve. And here is a full faceplate for a pump. You'll notice at this time that when I clicked on these HMI symbols, that the faceplate was immediately displayed. That is because I have now logged onto the system as a higher level, maintenance level access user. The idea is that there is a tab for each user role in the system. Most of what an operator will need can be found on the Home tab, which is the tab that we can see by default when we open up the faceplates. The next tab is the Maintenance tab. This is where a maintenance level user will find most of what they will need. So what does maintenance allow you to do? Maintenance allows you to do things such as substitute a value for this analog input on the left, tell the valve to simulate limit switches rather than use the real limit switch, and tell the pump to simulate the running feedback. The next tab on the faceplate is the Diagnostics tab. The idea of this tab is to make it easy for the user to understand when there are any issues with the device and if there's anything preventing this device from being operated. On the left here we can see that everything is good with our analog input. In the middle we can see that there are currently no issues with our valve and we can operate it, and the same for our variable speed pump. Next tab is the Alarms tab. Here we can see what alarms are currently active for a device, and on the left you can see there are no alarms configured for this analog input. In the middle you can see a large range of alarms have been configured for the valve and a large range of alarms have been configured for the pump, but none of them are currently active. For any item which has an analog input, there is also a trend tab. So our analog input has a trend tab and our variable speed drive has a trend tab. This is where we can bring up trends for our device, and what trends are available depends on the options we've taken out in our PlantPAx system. For these we can see that historical trending is not available because we do not have a historian for this system, so we can only access real-time trends. That is a trend which only updates when it's open. If we close this faceplate, the history that we see will disappear and we will just be shown the current data again. This analog input, however, does have historical trending enabled. So if we go into the trend button, you will see on here we have historical trends available to us, and we can bring up a trend where we can actually see the history back in time. We're zoomed right in here, so this is why the data is moving around so much. If we zoom out, we can see that data and we can go back in time and we can see the current value. For each of the faceplates, you also notice that there is a help button. This brings up the help for that particular device. Here's an analog input faceplate help. You have options about which help you wish to display. You can use the default help that we provide, which is a PDF document. You can make your own PDF document for all of the same types of devices and use that everywhere, or you can configure a device to use a specific help document. So it's possible that this analog input here uses a different help from this analog input here. As well as showing status information and allowing you to control devices, the faceplates also show you the configuration of a device, and if you have the permissions to do so, allow you to change the configuration. We access the configuration from the Maintenance tab. Here is the configuration faceplate for our analog input. Here is the configuration faceplate for our valve. And here is our configuration faceplate for our variable speed pump. As with everything in the library of process objects, If you don't have the security access to change something, then you have only the security access to view information. Depending on the library instruction that you're looking at, the amount of pages that you see in this configuration faceplates varies. The faceplates are split between maintenance, engineering, and HMI configuration. A key philosophy of the library of process objects is that it should be easy for a user to understand where problems are, what those problems are, and if they have the security to do so, have the ability to apply substitutions or enable simulation to get your process running. You should never have to need to open up those engineering tools and make changes inside a controller to get you through an issue on your plant or to understand what those issues are. So let's give a demonstration of this. Here at the moment, we have a healthy buffer tank and everything is normal. I am using Emulate 3D and the tanks and pipes catalogue to simulate my buffer tank process. So I've used catalogue items from the tanks and pipes catalogue to build this model very quickly, and I've then connected those catalogue items to the I/O of my PlantPAx controller. So my PlantPAx controller is sending out outputs and it's receiving feedback back from Emulate 3D. So let's use Emulate 3D to create an issue on our process plant and then demonstrate what we can do within the library of process objects to overcome it while someone goes and fixes that issue. Here we can currently see that the temperature of the inlet is 20 degrees C, and this is currently working normally. But with the Emulate 3D fault catalogue, we have the ability to simulate faults, and we can use that to place this analog instrument into fault, and then we can show some nice features of diagnosing that fault in the library and overriding the system to get us going. So firstly, I'm going to go in and select this analog input. I have previously set up an analog false fault on this device so that we can force it to a particular value, 3.5 milliamps, to simulate an instrument failure. So let's turn this fault on. You'll see that it's highlighted to show that this fault is active. And now let's go back into our PlantPAx system. Here we can see that the inlet temperature has now failed. We have an indicator to show that there is an issue with this. And if we bring up the faceplate, we can see that there is a signal failure active. So this is showing one of the key features, in that if there's any issue or alarm active, it will always be shown at the top of the faceplate. And if there are multiple alarms or issues active, this will be a multi-line display. So what can we do about this failure? Well, we know that the process is currently working correctly. We can send some monitor the real plant and they can see that the temperature is actually 20 degrees. So what we can do is we can use the substitute feature in the library of process objects to simulate this value to get our process running while the instrument is repaired. To do that, I need to be logged on as someone who has maintenance level access or above, which I am. And then from the maintenance tab, I can select to substitute this process value. You notice that we're asked, are we sure we wish to do this? I am. And then we can put a value in here to get our process running. We know by monitoring the physical plant that currently 20 degrees is present at that location in our process. So we're going to put 20 degrees into here. Now we can see that that value is being used by the system. Well, what if I'm an operator looking at another part of the plant? How do I know that there is a substitution in place and that a substituted value is being used in the system? Well, the library of process objects provides us a great feature that makes it easy for us to understand when there are not normal things going on in our system, there are substitutions in place, there are prompts that our operator needs to pay attention to, or there are alarms or interlocks or permissive conditions in place. From the top level 1 display here, we can see that there is currently a substitution active in the buffer tank, and that's being indicated by this little spanner symbol here. If we click on that, then we can see go straight to the buffer tank, and we have two choices then for how we find this issue. We could scan around all the different values on the screen until we find it. That's fairly easy in this case. We can see it's this one here. But if we had a more complicated system, or we had level 2 and level 3 displays, that might take a while, and we have a much quicker and faster way available to us in the library. We have the tree view object, which shows us a structure of our process plant. The organization, ownership and arbitration feature in PlantPAx allows us to structure our plant into a tree view in whatever structure that we like, to show the layout of our plant and allow our users to see the status in those areas and navigate quickly to any issues. Here we can see that in the buffer tank area we have the spanner symbol active, and that's active in our unit, and we can then drop down into that unit. We can see that that's active in the inlet area of our buffer tank. We drop into the inlet area, then we can see that it's active for this device. This structure is completely flexible. You can structure that how you wish. If the user didn't know what these symbols mean, then again we can go into our help and we can see that means there is a maintenance bypass active. So this tree view is telling us that there is a maintenance bypass active in the buffer tank area. It's in this unit, it's in the inlet area of that unit, and it's for this particular device. And by clicking on this device, we can go straight to the faceplate to see the detail. We can see that there's a signal failure active for this device, and we can see on the maintenance tab that the maintenance bypass is active. So this is what we call the breadcrumb trail. It's taken us directly to where the not normal situation is, or where there's an issue, an alarm, an interlock. So let's go and repair this instrument. For us, that's an easy thing to do because we can go into Emulate 3D and we can remove the fault to repair the instrument. If we now go back into our PlantPAx operator workstation, we can now see that the value here is operating correctly. So we can see that instrument is being repaired, and I can now choose to switch back and use it. And now you can see that the status information is updated and everything's back to normal. Another key feature of the library of process objects is that everything that the user does from the HMI in terms of commands on objects, or changes by a high-level user in terms of configuration, goes into an audit trail. So let's have a look at the audit trail for the PV substitution that we've just demonstrated. The audit trail is logged into a Microsoft SQL database, and that means you can use Microsoft SQL Server reporting services to view the audit trail. So here we can see the audit trail. You'll see that each command or setting change that's undertaken on the library objects is logged with a message that starts with RAP command or setting, giving a definition of what's happened. You can also see the logged in user that undertook that action. You can see the location. This is the name of the operator workstation, which you can choose when setting up your PlantPAx system. And here we can see that the time that this occurred. So here we can see when we commanded that inlet temperature to use a substitute process value. Here you can see when we set that substituted value to 20 degrees centigrade from minus 3.125 degrees centigrade. And here you can see us switching back to use the input PV after the instrument was repaired. As well as looking at these in a textual report format, we can also look at these on a trend. So let's go and open up a trend and look at that audit trail. I have already created a trend template, so let's open that, and here we can see data being logged in our historian together with data from our alarm system and audits. Let's go back and look at the last 30 minutes of information, and here we can start seeing those audit actions. Just going to Move time across a bit, go back a little bit further. Here we can see where we actioned that substitute command. Here you can see when we then put in our substituted value. And here you can see when we switch back to using the real process value. You can also show alarms on this trend from our alarm history, as well as current data values in the controller and data from our historian. Now let's have a look at an example of overcoming a broken limit switch for a valve. Let's have a look at the line 1 supply valve. This is currently closed, and it is therefore closed in Emulate 3D. This is currently operating normally, so if we come and command it to open, you'll see that the output from the valve energizes. Emulate 3D moves the valve to the open position within the configured transit time within Emulate 3D, and the valve is now open. Let's now close this valve and watch the same thing happen from the transition from open to close. Okay, the valve is now closed. But this time, let's set up that the valve open limit switch is going to break. Using the fault catalog in Emulate 3D, we can configure whatever fault we like on this valve, where we need to specify that either commands to the valve go to a certain state, or feedbacks from this valve back to our controller go to a certain state. In this case, I've set a digital force low fault to set the open feedback from this valve to the controller is going to be forced into the off state. So Emulate 3D will receive the command from the controller and it will move the valve, but it won't set the open limit switch input into the controller once the valve reaches the open limit or open position. So I'm going to enable that fault. You see that valve is now highlighted to say that there is a fault. I'm going to go into our PlantPAx operator workstation and command this valve to open. So again, valve command is energized. Emulate 3D has opened the valve, so liquid would flow through, but the valve feedback won't be coming back. So eventually we will get a transit stall alarm on that valve because the feedback didn't come back. Now we know that the valve is open and we could put things in place to make sure that the valve is in the right position. So how could we overcome this fault while we repair the valve limit switch? Before that, we can use the substitution feature in PlantPAx. So firstly, I'm going to acknowledge this alarm to make this valve healthy again. But then I'm going to come into the maintenance tab, and knowing that the open feedback is broken, I'm going to tell this valve to not use the actual valve open feedback, but to simulate that to get our process running. You see now that the spanner symbol has appeared to say that we have that substitution active. If we now go back to the home page and open our valve, and we see the valve is commanded to open, we can see that valve is now open in Emulate 3D. If we come back into the operator workstation, we can see that the valve is now open and our process is running. Let's now look at another powerful feature of the library of process objects that is used by PlantPAx. Let's try and close this outlet valve here. If we go into the faceplate, we notice that we're unable to close this valve. This is because the valve is currently owned by the program. For all devices in the library where you can control the device, you have outputs from your controller that control it. There is an ownership model which specifies who's in control of that device. The base level is operator mode, where the user logged onto the HMI, if they have the necessary security permissions to do so, is in control and can decide what state this device should be in. The next level up is program mode, where the controller is responsible for deciding what the desired state of this device should be. For both operator mode and program mode, you can lock them into that mode. And this is what we can see here. The program has locked it into program mode so that it cannot be put into operator mode by the operator from the HMI. The operator can't take control of this device. If the operator could have put it into operator mode, then they could lock it into operator mode to prevent the program taking ownership of the device. There are then other modes that you can use, which are optional. Above program and operator mode, you have override mode. This is logic within the controller that can override program and operator mode and put this device into a particular required state. Then you have maintenance mode. This is where someone, a higher level user with higher level security access, logs onto our operator workstation and can put the device into maintenance, and they can override program and operator mode. For each device, you can decide whether override is at a higher level than maintenance, or if maintenance is a higher level than override. For each device, you can put it out of service. This is where the device is disconnected in the field. You no longer wish to control it, you no longer wish to see its state, and you no longer wish to generate alarms for it. You also have hand mode. This is where the device can be locally controlled and you just wish to follow the state of the device, but you could no longer control it from the HMI while it's in hand mode. And then finally, there is external mode. This is where you have two locations of control for the device. As an example, you might have a local control room and a remote control room. When the device is not in external mode, it's controlled locally, and when it's placed into external mode, it's under the control of the remote control room. So our device is currently in program locked, and we're unable to command this valve to close. So let's now use the maintenance override feature in the library to override this and command this valve to close. The first thing I need to do is I need to log in as a user who has the ability to place this valve into maintenance. In my case, I'm going to log in as a plant maintenance level user. The library of process objects supports both security roles and security areas. A security role defines the level of access required to undertake each command on the faceplates for these library objects. The library comes with an out-of-the-box setting for these, and you can change that. So you can say things that are out of the box that require maintenance level could be changed to require maintenance supervisor, as an example. The area-based security allows you to split your system up into different areas, and then for those areas define different levels of security for a logged-in user. For example, in this system we have 5 different areas of our plant. We have the feed drum, the storage tanks, the batch tanks, the process plant, and the buffer tanks areas. I can define that my user can be an operator in the feed drum, an engineer in the storage tanks, and have no access, as an example, in the other areas. But in this case, I've logged in as a user who has maintenance level in all these areas. Now we've logged in as a maintenance level user, let's go into the faceplate. You'll notice that we go straight into the full faceplate because we've logged in as a higher level maintenance user. We'll go into the current mode for this device. We'll go onto the maintenance tab. We'll now place this device into maintenance. So now we can override this device and put it into the required state that we wish from the operator workstation. Let's command this valve to close. As you will hear, that's caused an alarm because it's tripped this pump, and we now have a medium level alarm in our system. But what if I was on another part of a plant or looking at a screen in a different area? How would I know that there was an issue in the feed drum? Well, the HMI framework that we provide with PlantPAx makes that easy for us to understand what's going on. Here we can see from our top level, level 1 display that we have a medium level alarm currently active in the level 2 feed drum area, and that's indicated by the yellow flashing border. The colour changes based on the priority of the alarm, as well as the alarm symbol that's displayed. So I can see that there's an alarm active in there. I can either click on the level 2 feed drum button or the level of the feed drum area to go into that area to understand more about where the alarm is. And then I've got a couple of options on how I find that alarm. I could go into the level 3 display, and I could go around looking at all the objects on the screen to understand where the issues are. Here I can see that there is an issue on the unit and there is an issue on this pump. Or using the Organization, Ownership and Arbitration tree view feature in the library, I can bring up the tree display for the current area of plant that I'm in, and very quickly I can understand where the issues are within this area. I can see that I have issues within my feed drum area, they're within my V102 unit, and they are occurring on this particular pump as well as this particular valve. If I didn't understand what these symbols mean, then the help tells me. I can see that there's a device not ready to operate, I can see that there's an object not usable by its parent, and I can see that there is a medium priority alarm active. From here then we can go straight to the faceplate to understand the issues on this particular device. So here we can see straight away that there is an interlock trip active. This is shown in the alarm tab, and on the diagnostics tab we can see that we're not able to start this pump because there is an interlock. Another option that we have is that the engineering tools that we provide with PlantPAx will set up the alarms for devices so that when we double click on them from our alarm banner or select them in the alarm summary and execute the command configured for them from here, they will take us to the display where the alarm is and bring up the faceplate. So as you can see, we can very quickly get to the issues on our plant and understand what they are. So we go into the faceplate and we can see that there's an interlock trip active for this pump, and I can see that there's an alarm active for this interlock trip, and I can see that I'm not able to start this pump because the interlocks are not okay. But what is the interlock that's causing this interlock trip? Well, from this faceplate we can click the interlock button to bring up the interlock faceplate for the device, and here we can see all the interlocks that are configured, which ones are active. It's the ones highlighted in a lighter colour, and which ones were the first ones to trip and generate the interlock, the ones with an X beside. So here we can see that the valve not open interlock is the cause of this problem. And from here we can actually click on these interlocks to take us to the faceplate for the device that's causing the interlock. So if I click on the valve not open, I will bring up the faceplate for that valve. If I click on the high pressure, I will bring up the faceplate for the pressure analog input that generates that pressure high alarm. Now the quickest way to overcome our interlock is to remove the maintenance for this device. By doing that, we can see from here that it will go back into program mode. The logic within our controller has been configured then to command the device into the required state. So the valve will then be put back into the correct open state. So let's do that. I'll remove the maintenance command. You'll see that it goes back into program, and we can see that this valve then opens. Our interlock is not a latched interlock. So as soon as the valve opens, the interlock is removed and our pump starts. Each interlock is individually configurable as to whether it is latched or not, and if it's latched it will require a reset. It's the same for whether an interlock is bypassable or not. They're all individually configurable. And you can have up to 256 interlocks configured for a device. So now that interlock has been removed, the valve is open, the pump is running, but we still have our interlock trip alarm telling us that there was an interlock, and we can acknowledge that from our faceplate, or we can go into the alarm summary and acknowledge it from there. Let's do that for this case. So I'll select the alarm and I'll acknowledge it. And if we go back to our feed drum, we'll now see that all the indicators on the banners have disappeared. Everything is now healthy in this area, and the alarms have disappeared from the feed drum area. So everything that the user did from the operator workstation goes into the audit trail. So let's have a look at that audit trail for the demonstration that we've just undertaken. The audit trail is logged in a Microsoft SQL Server database, and that means we can look at it using Microsoft SQL Server reporting services. So let's open up a SQL Server reporting services report for the audit trail. Here we can see the audit entries that are generated for the demonstration that we just undertook. So let's finish our introduction into some key features of the library of process objects and the PlantPAx HMI framework by looking at some of the statistics that you can collect for pumps and motors and variable speed drives and valves in the PlantPAx library, and at the command confirmation features that are available for devices that you can command in the library. So for each motor, variable speed drive and valve, you can choose to add a statistics object if you wish. You access these statistics objects from their faceplates. So from the motor or variable speed drive, we go into the maintenance tab on the faceplate, and there we will find the button to access the statistics object if it's been added. For a pump, here we can see the statistical information that is collected for that motor or variable speed drive. We can see the current time it's been running. We can see the maximum amount of time it ran in one go. We can see the accumulated running time, and we can see the numbers of motor starts or attempts to start for that device. The same for a valve. If we go into the faceplate, onto the maintenance part of the faceplate, we can access the statistics object for the valve, and here we can see the statistical information that's collected for a valve. We can see we get information about the number of open strokes and closed strokes undertaken on that device. We can see if any of those failed to complete. We can also see if any of those were slow. This is where the time taken to perform that stroke was slower than a configured time. And you can set up an alarm on that if you wish, and use that to indicate that maintenance is required on that valve. You can also see information about times in the different states. How long was that valve in closed, closing, opened or opening states, how long it was last in that state, the maximum time it's been in those states, and the total time and average time that it's been in those states. Now let's look at the command confirmation options for any device that is commandable in the library of process objects. During these videos, you've seen commands just happen when we had the permission to do so. That is the default setting, but for each library object which is commandable, you have a number of options, and we can see the configuration for each device from its maintenance tab, the advanced properties faceplate, the HMI configuration tab of that, and the second page area, where we can then see the operator command confirmation setting. This setting is individual for each device, so this valve can have a different setting from our pump. At the moment we see the default setting of none. Commands just happen when we have the permission to undertake them, but let's see what the other options look like. The first thing I need to do is log in as an engineering level user who has the ability to change these settings for this valve. So let's place this device into command confirmation. We'll move this over here so we can leave that up while we demonstrate that. Let's then undertake a command on this valve. To do that, we need to put it into maintenance because it's currently locked into program mode. Now we have it in maintenance, we can override program mode and we can close that valve. But here you'll now see that we need to confirm that we wish to do that. I shall say yes, I wish to confirm to do that. We'll close that valve. We can now see that that's commanded to close. And then we'll do the same for the valve open. Here you can see again, we need confirmation. We'll acknowledge that. And that will then move to open. So that's what the command confirmation option looks like. The next one is performer e-signature. The person undertaking the command needs to put in an electronic signature for why they're doing it. So let's show an example of that. Again, we'll close this valve. But now you can see that I'm being asked to review the action I'm undertaking. It's going to use the currently logged in username for this operator workstation for that electronic signature, but it's requiring me to put a comment in here. So I'm going to put in here a suitable comment, test valve close. As we have a valid electronic signature, that command has now been actioned and the valve is closed. Let's now show the final option, performer and approver. This is where both the person that's undertaking the command needs to undertake an electronic signature and a separate approver, someone who's authorized to approve electronic signatures, also has to sign off that that can happen and then it will happen. So let's now open this valve. Here we now have the dialog for the current person undertaking the command, the performer needing to fill in their password this time, and the comment as to why they are doing that. We'll accept that. So we've successfully signed it off. Our password is correct. That's now been logged. We now need someone who has the ability to countersign that action. In my case, managers have that capability. When you set up your PlantPAx system, you configure the users or user groups who have this capability. And I'm going to put a comment in here acknowledging basically that is allowed. So approved, and we'll accept it. Notice that I could also reject it, and that rejection would also be logged. Now we've accepted it, the valve now opens. So I'll return this device back to the default of no command confirmation. I'll remove our maintenance. That device is now back to normal. All those changes of the command confirmation and those commands go into the audit trail that we've been looking at throughout these videos. So let's go and have a look at that audit trail for those sets of actions that we've just undertaken. So here we can see the audit entries logged in a textual format for that demonstration that we've just undertaken. At the bottom here we can see when we first enabled command confirmation for our valve, that the plant engineer was a logged in user that did that and where they did it from. The name of my demo operator workstation. This can be set to a meaningful name when you install your PlantPAx system, and here we can see the location, well, the time that happened. Next we can see then we place this device into maintenance. We close that valve to show the command confirmation prompt. We open that valve to show the command confirmation prompt. We then switched the command confirmation to performer e-signature. We undertook a close of that device, and at the same time, both logged at 12:31:33, you can see the electronic signature that we filled in for that. So we can see that plant engineer performed that, the comment that I typed in, where that was done from and when. Then we can see when we switched on performer and approver command confirmation, we can then see where we performed the electronic signature. This is by the performer, so this is the first part of the electronic signature. The person undertaking it puts in their electronic signature with their comment. Then at the same time as the authorizer electronic signature, the approver, we have the command because it was approved. Then we switch that valve back to not requiring command confirmation and we release the maintenance control. Again, these can also be shown on a trend. So let's open up a trend that I've already configured to show the audit trail information together with information from our historian and from our alarm history. Here we can see all of these audit actions being shown here, and we can go and look at each of those and see those in relation to other data on the trend for analysis of events on the system.